Today's lecture will be on friction, and what we're going to be spending our time on really is just section 9.1 in this particular video. We're going to look at just the basic concepts of friction, and then I will go over some examples after this video on looking at problems with just one contact surface problems, which are some of the easiest problems, then looking at multiple contact surfaces that slide simultaneously, and then last we're going to look at tipping versus sliding motion. The next lectures after this will cover the topics of multiple contact surfaces and then belts. So have you ever had like a box on the floor or some object on the floor, a chair or something on the floor, and you started pushing on it, right? And you kept pushing and pushing, and it was very difficult to move, and it wasn't moving, but all of a sudden it started to move. Sometimes objects start moving slowly. Sometimes they start moving very quickly. If we look at a free body diagram of this, of what's actually going on in our situation, we have this type of situation here. If we zoom in a little bit on this free body diagram, we see we have this normal force. This is the weight of the object itself. This is the force we're pulling on. This is what we call our frictional force. And then we have our normal force, which is the reaction force back up on it. This is our basic free body diagram. Note it is specifically placed, this normal force on the surface is specifically placed not in the center. Okay, and we'll get to more of that later. We don't really know exactly where that normal force is because our frictional forces that are going on in here may have some shape to it, and they aren't uniform. So because of that, our normal force may be at some other location. So like I said, we start pulling and pulling on this force F. We keep pulling with a higher and higher force, and then all of a sudden it starts to move. We can see that with this diagram here. We are pulling and pulling, nothing happens, and then all of a sudden it starts to move. And we either get a situation where we have to continually add a little more force to it, or that force that we're at just kind of lets it move and we kind of can keep moving with that same force. But typically we see this type of situation here where all of a sudden it goes and then the force actually drops off. It's a little easier to push this object. But any one of these cases is possible. So the question comes in, what is this frictional force, right? That frictional force could be any value along this graph here, right? Until it gets to this point here on the top, which we call impending motion, right? And once it starts moving, then our force changes. Well, how do we come up with this force, and what is the equation of this force? It's very interesting to note that this force is this friction force that friction force produces slipping is reasonably accurate if we look at this equation. If our friction force or our slip is equal to some coefficient of friction times that normal force. And this was discovered way back in 1699. So this frictional or coefficient of friction really depends on a few things. It depends on the type of materials that are contacting each other. It depends on the surface roughness or how smooth that surface is. It may depend on the environment like humidity, temperature, that type of thing. And other factors such as oils and lubricants may make a difference in our surface's coefficient of friction also. The one thing that's interesting is that this coefficient of friction is assumed to be independent of two things. One is area of contact, so how much area is contacted. It's independent of that. It is also independent of any sliding velocity. If it is actually moving, the velocity of it doesn't play into it. Now, the temperature may go up as we have the sliding velocity, and then we'll have some environmental effects, but otherwise the velocity itself does not have any effect. So again, if we look at this, we see that we have this force, and as we continually pull on it and pull, finally gets to this point F sub s, Again, that is called our impending motion or impending slip. And then at that point, we can solve for our frictional force is equal to our static coefficient of friction, mu s, times the normal force. Typically, we might have this rapid loss in frictional resistance that occurs sometimes, not always, but that is more typical. And in that case, then we have this equation here for our kinetic friction, or friction for motion, using the coefficient of kinetic friction. Another way of looking at this diagram that we see sometimes is we will see something like this, where we have our F, our frictional force, and what we'll call our pulling force. So if I have my object again, and I am pulling on it with some force P, and I have my frictional force F, right, and then we have our normal force and our weight coming down. We have this relationship also. Another way of looking at this is this relationship between the frictional force and our pulling force, where they're actually equal to each other. This angle is 45 up until impending motion, and then our frictional force may drop off on us at that point, okay? And it may change, but up until that point, they're equal to each other. But after that point, then these equations come into play. If you go online or look in your book, you will find this particular table, 9.1 in our book, a number of coefficients of friction that are given to us. This is looking at aluminum, and aluminum itself has a range of coefficients of friction. It could be aluminum on steel, and so on and so forth. So these are all based either on themselves or compared with steel. You will see, though, that there are cases where our coefficient of friction is greater than 1, right? We see rubber tire on pavement. We have a very large coefficient of friction there. Even iron on iron itself can be greater than 1, or iron on mild steel, which mild steel is iron, that is greater than 1 also. So we do have occasions where our coefficient of friction can be greater than 1. Okay, so finally we have Coulomb's law, which again states that our frictional force is less than or equal to our static coefficient of friction times the normal force. And that is less than that up until impending motion. Once it's just about ready to move, then it's equal to each other. The problem that typically students get is they think that this force F is always, this frictional force is always equal to our static coefficient of friction times the normal force, and that is just not true. So this is not always equal to mu Sn. This is only for impending motion. Otherwise, it is less than this value. The other important thing that we need to consider is that the direction of our frictional forces is always trying to be opposite or oppose the relative sliding motion. So it wants to resist sliding motion, or any motion at that point. And that sliding motion really should be sliding. And last, we can look at this, and typically we kind of don't really always use these absolute value signs. We just know which direction that it is, and it's understood that this mu sub s is for static friction, and then if we have sliding, up to impending motion, and then if we have sliding, then we use our kinetic friction. Last, I just want to kind of talk about how do we solve problems with friction. Again, when solving problems with friction, with frictional sliding, We will assume the directions for impending motion when drawing a free body diagram, so we need to assume that direction. And after our analysis is complete, we may need to look at if our assumptions were correct. Using this approach, we will be able to satisfy the requirements of frictional forces, that they oppose the directions of relative motion, and we may ignore the absolute sign on Coulomb's law. All right. I encourage you to watch the next videos. There should be 3 videos following this. One is just a really good, simple frictional sliding force problem. Then there is one with tipping versus sliding. That's a consideration we need to look at. And then last, it is multiple surfaces that all slide simultaneously. So these are 3 really good example videos to watch. If you have any questions, always drop me an email and I'll get back with you.